Today, we're going to dive into a really clever bit of data science magic called the CountMin Sketch. It sounds a little intimidating, I know, but it's a tool that lets tech giants solve a problem that seems pretty much impossible. And we're going to see exactly how it pulls it off.
So let's just start with a huge question. Imagine you're a company like Twitter or Google or TikTok. You've got this absolute fire hose of data blasting at you every second. How in the world do you keep track of what's trending, of the frequency of millions or even billions of different items, without your memory costs just going to the moon? It sounds like it can't be done, but there's a surprisingly elegant answer.
And this isn't just some academic thought experiment. It's a real core challenge in the world of big data. We call it, well, the big data counting problem. And it's a hurdle that pretty much every large-scale system has to figure out how to jump over.
Seriously, just try to picture that constant, overwhelming stream of information. All the user clicks, all the search queries, all the network packets. If you tried to use a simple, straightforward tool like a hash map to keep an exact count of every single unique item, well, your memory usage would just explode. For most real-world applications, it's completely infeasible. Okay, so if exact counting is off the table, what's the plan B? We need a totally different way to think about this. And this is right where the genius of the CountMin Sketch comes into play. It doesn't solve the problem with brute force, it solves it with a really clever probabilistic strategy.
So what is this thing exactly? A CountMin Sketch is a special kind of data structure that doesn't give you perfect exact counts. Instead, it gives you very, very good estimates. And here's the crucial part. It does this using a small, fixed amount of memory, no matter how many millions of unique items you throw at it.
The core trade-off here is just brilliant. You give up the guarantee of perfect accuracy, and in return, you get absolutely incredible performance. We're talking lightning speed and tiny memory usage. This is the kind of deal that takes a problem that might need terabytes for an exact solution and shrinks it down to something that can fit in just a few megabytes. For any system at scale, that's an absolute game changer.
All right, let's pull back the curtain and see how this thing actually works. The mechanics behind the magic are surprisingly simple, but man, are they clever.
At its heart is just a simple grid of counters, like a little spreadsheet with everything starting at 0. This grid has a certain number of rows, which we'll call D for depth, and a certain number of columns, which we'll call W for width. But the real secret sauce is that each and every row uses its own unique, completely independent hash function. So, there are two main things you do. First, when a new item shows up, let's say the word apple, you hash it once for each row. So if you have D rows, you get D different positions in the grid. You then just go to each of those positions and you increment the counter. That's it. Later, when you want to ask, hey, how many times have I seen apple? You do the exact same hashing process to find those same D counters. But, and here's the key step, you don't add them up. You take the minimum value you find among them.
Now you're probably asking, why the minimum? Think about it. When you increment a counter for apple, some other item like orange might randomly hash to that exact same counter in one of the rows. That's called a collision. This means that counter's value is the true count of apple plus some noise from other items. Collisions can only ever increase a counter, they never decrease it. So the brilliant insight here is that by taking the minimum across all the rows, you're picking the counter that was the least polluted by all those other collisions. It's your best possible guess.
And this leads us to the single most important guarantee of the CountMin Sketch. It might overestimate, sure, but it will never underestimate the true count. The value you get back is always the real count or higher. And that one-sided error makes it incredibly predictable and super useful.
Now, this isn't some one-size-fits-all tool. The beauty of this whole thing is that you can actually tune its accuracy. You get a couple of dials you can turn to get exactly the performance you need for your specific problem.
And those dials are just the width and depth of our grid. If you make the table wider by increasing W, you're giving items more space, so the chance of two different things hashing to the same spot goes way down. That directly improves your accuracy. Now, if you make the table deeper by increasing D, that's like getting more independent opinions. It lowers the probability that all of your counters for an item are badly polluted at the same time. This increases your confidence in the result.
So let's just summarize what you get. The time to update or query something is proportional to the depth D, which is incredibly fast. The space it uses is fixed by the grid size W times D. And by choosing those parameters, you get a formal mathematical guarantee. You can control the maximum error, which we call epsilon, and your confidence in that error bound, which we call delta.
Okay, one really important thing to remember here. The standard count-min sketch is designed for what's called the cash register model. You know, a cash register only adds to the total. The count only goes up. It's not designed to handle subtractions or negative counts, because that would completely break that never underestimate guarantee.
So now that we know how it ticks, let's talk about where you'd actually see this thing in the real world and how it stacks up against other common tools you might have in your toolbox.
You'll find this algorithm absolutely everywhere in large-scale systems. Network routers use it to find the heaviest data flows without having to store everything. Databases use it to quickly guess how big a query result will be so they can run things efficiently. And, of course, analytics platforms use it to find those trending hashtags or products in real time. It's even perfect for things like rate limiting at scale. And to really get why it's so powerful, let's compare it. A regular hash map gives you perfect accuracy, which is great, but its memory just grows and grows with every new item. A Bloom filter is even smaller, but it can only tell you if an item might have been seen before, not how many times. The count-min sketch hits that perfect sweet spot. It gives you approximate counts, and its space is determined by the accuracy you want, not by the number of unique items you see.
And hey, here's a quick pro tip for you. There's an optimization called conservative update. When a new item comes in, you first query what its current estimated count is. Then, you only increment the counters that are equal to that minimum value. This helps to reduce how much pollution you're adding and can often lead to significantly better estimates in the real world.
So, if you're ever in a technical interview, here are the absolute key points to remember. 1. It gives you fast, approximate counts with a one-sided error. 2. It never, ever underestimates. 3. You can tune its accuracy versus its space usage with its width, W, and depth, D. And 4. It's perfect for streams where counts only go up, that cash register model. Nail those points, and you'll be in fantastic shape.
I'll leave you with a final thought to chew on. We know the sketch can overestimate, but can you think of a system where always erring on the side of a higher count might actually be a desirable feature and not a bug at all? It's a pretty interesting design question. Thanks for watching.